In this example, we're going to be trying to figure out all of the values of r such that y is equal to x raised to the r power is going to be a solution of the given differential equation. This is x squared y double prime plus 2xy prime minus 6y is equal to 0. Given that this is a second order differential equation, first thing I'd like to do is start with our proposed solution and take a couple of derivatives. Now, because it is a power, we are going to employ the power rule twice. Multiplying by the current power gives us r, and reducing the power by 1 will give us r minus 1. Taking a second derivative, we'll repeat the process. This r now represents a constant coefficient, and we apply the power rule once again. Multiply by the current power and reduce the power by 1. I'm going to take all three of these expressions and plug them into the original differential equation. So x squared y double prime plus 2x y prime minus 6y would become x squared times y double prime. That'll be r times r minus 1 times x raised to the r minus 2 power plus 2x times y prime, which will be r times x raised to the r minus 1 power, minus 6 times the original function y, which is x raised to the r power. Now, using the fact that we have a lot of x's being multiplied together here, we can combine those. The first term, if I take my x squared times x raised to the r minus 2 power, I can add those two exponents together to get an x raised to the r power. Something similar will happen on the second term here, where I take x to the first power times x raised to the r minus 1 power and add those two exponents together to get x to the r minus 6 times x raised to the r power. In this form, you'll notice that all three of these terms have an x raised to the r power in common. As such, we can factor it out. When we do factor it out, we'll be left with the following expression: r times r minus 1 from these terms back here, plus 2r minus 6. Now, do bear in mind all of this was initially equal to 0. What we're going to be doing is solving for r, because that's what the original problem said: determine all values of r. So, leaving the x to the r on the outside, I'm going to distribute the r through the first set of parentheses, and then combine like terms inside that set of parentheses, leaving us with the quadratic expression r squared plus r minus 6, which factors pretty nicely, so we'll go ahead and do so. That'll be r plus 3 times r minus 2. Applying the factor theorem says that if r plus 3 is a factor, that means that r equals negative 3 is a solution. And if r minus 2 is a factor, then r equals 2 is going to be another solution. Now, this is technically all that was being asked of us: determine all the values of r, but really we can break this down into two different solutions. X to the negative third power would be one solution, and x squared would be the second solution. I get each of these by plugging the values of r that we just got back into the original assumption. Original assumption is that y equals x to the r is a solution. In terms of a linear algebra, this would be two linearly independent solutions of the original differential equation.